My name is Junpeng Wang, a student at Fudan University, and it's my pleasure to give this presentation. This is a work from Fudan University and the University of California, Irvine. Our work is invisible probe timing attacks with PCIe congestion side channel. Let's start with a little background about PCIe protocol. PCIe is the de facto protocol to connect CPU and peripheral devices, and numbers and kinds of peripheral devices connected to CPU are increasing, like GPU, network card, and SSD. But PCIe interfaces offered by CPU increase slower, so there is a gap. Fortunately, PCIe is designed like a network protocol. We can use switch to sharing interfaces, like PCH and PCIe switch. PCH supports interfaces for the lower speed devices like flash, Ethernet card, and so on. And PCIe switch stays more closer to CPU and it connects to the faster devices like GPU and RDMA network card. We term it the RO switch. There are always problems when sharing hardware resources. When the different devices send data through the PCIe link at the same time, the bandwidth may be not enough and the throughput or some critical application will decrease. The user will feel long latency. Even worse, malicious users can launch a denial of service attack. In the worst case, the user's secret information will be leaked, and our side-channel attack will prove that. Here is our threat model. There are a pair of our devices. One interacts with the attacker and another interacts with the victim. Both devices share the same IO switch, which connects to the upstream CPU. The attacker cannot access the victim's data or code directly. We use our side-channel attack to infer the victim's secrets at the sharing channel. Our attack procedure is simple at high level, but we still face some challenges. Firstly, there are many choices of the probe. For example, different IO APIs, but they need to fulfill the below promise to measure the delays. Firstly, probe should complete each request within a short interval, and the probe should produce a stable latency. Congestion level should be proportional to the probe delay. The regular measurement tools provided by the operating system cannot provide enough accuracy. So we need high-resolution tools to capture the weak signals from user-sensitive activities. Thirdly, the probe's attacker issues might interfere with observations because the attacker cannot directly measure the victim's device. To solve those challenges, the probe and the inference methods have to be carefully designed. Here is our contribution. We indicate the problems of sharing PCIe devices. We design new side-channel attack based on PCIe congestion. We develop effective attack strategies and evaluate them on true victim tasks. We will explain the details later. So why are the data leaked? We use a demo to explain the reason. There is an attacker with a clock and a victim. They access data from their devices at the same period of time. When the devices produce too much PCIe traffic, the channel will be congested. This graph is about the relationship between traffic and latency. If there is just an attacker using the channel, attacker feel short latency, and if both attacker and the victim are using the channel, they will feel long latency. We depict the columns in different shades and colors. We make some assumptions to make our demo simple. Firstly, we assume that the buffer size of the upstream port is 1, which means that only one packet can be sent once at a time. We assume that the IO switch has enough buffer and it consumes no time to send packets from the device to the IO switch. We assume that the user spends no time to get the data. So when time is T0, the attacker wants to read the packet. Since PCIe employed credit-based flow control, the receiver notifies the sender the size of the receiving buffer result with credit. Since there is no other traffic, she will get the credit and send data. At time T1, she gets the packet and calculates a short latency. Also at time T1, both the attacker and the victim want to read the packet, but only one can get the credit. We assume that victim gets it and the attacker stores. When time is T2, the victim finishes his reading. The victim gets the data and the attacker gets credit. When time equals T3, the attacker gets her packet finally and calculates a long latency. And the attacker wants to access another packet at time T3, and he gets the credit soon. She gets the packet at T4 and calculates a short latency. So here is the answer. The attacker can know when the victim is active. When the attacker gets a high latency, she knows the data is moving. How to monitor the leaked victim behaviors? The answer is in the demo, by monitor the data movement activities. There are two steps. The first step is probe. Attacker accesses the data through the PCIe channel ceaselessly and makes the channel congested. Then she records latency between two operations using teaming instructions like RDT at CP. The idea to write the probe code is very easy, but the real probe is a little more complicated. We actually operate on the QPLs to make use of kernel bypass mechanism to generate stable and high-frequency traffic on the channel. In this way, we can make our probe more stable and the channel more congested. The second step is infer, and it's also easy to analyze the latencies. A higher latency means that data is transmitting. Then we can get a sequence of data movement activities about victim behaviors. However, how to design the probes depends on attack scenarios, and we implement our attack in two scenarios. In the first scenario, the sharing out switch is PCIe switch. When the victim uses GPU on the server, the attacker can use an RDMA network card on her machine to probe the RDMA at a high speed on the server, and then infer the victim's secrets. As to probe implement details, we implement our probe under InfiniBand protocol, and set a fence after each request to make sure the request comes one by one. The sampling rate can be as high as 770 kilopoints per second. As for timing, we set a flag in the sending queue and collect the hardware timestamps to timing. And the resolution of the timestamp is 63 nanoseconds. In the second scenario, the sharing out switch is PCH. When the victim is using an Ethernet card, the attacker can probe the NVMe SSD at a high frequency to introduce PCIe congestion, and then measure the delays at the same time. As to the probe implement details, we use Storage Performance Development Kit SBTK to operate on NVMe, and the SBTK can achieve a low latency and a kernel bypass I/O. And we commit and complete tasks on QPLs in memory and write memory mapped registers MSR to notify NVMe. It is called doorbells. The sampling rate is more than 812 kilopoints per second. The timing instruction is RDT at CP, and the resolution is CPU cycles. The details and the pseudocode can be found in our paper. What information can we infer from data movement activities? Let's imagine that victim's device may be a GPU or an Ethernet card and so on. If the victim is using GPU, it will read the password input in the monitor or the web pages. We can also use it to train a machine learning model. If the victim is using an Ethernet card, it will transmit web pages packets or packages related to SSH to CPU or memory. All this information can be inferred from the delay sequences. We can infer secret data movement activities from three tasks: user input keystrokes, web page browse, and machine learning model trained by GPU. In our experiment, we can infer all the three kinds of information successfully from scenario 1 and only web page information from scenario 2. How to infer secrets depends on delay sequences of specific tasks. We will introduce that by demos. The first task is user input inference. The victim may input a password in a payment website. The keyboard will generate an interrupt to signal CPU, and CPU will send a character or just a black dot to GPU to render it. Now here is the demo. We can find that each key will introduce a period of high latency, and the attacker will learn the keystroke sequences after analyze it. In the actual attack, we find the input prompt blinking and noisy, but we can remove it since the time gap is fixed. Here is the web page inference task. Imagine that we have two websites, fudan.edu.ca and ssTube.com. The first web page has the images and the second web has a video. Victim access the website from internet, so data packets will transmit from internet card to memory or cache, and the victim use monitor to browse the website. So some objects will be sent to GPU to render. How does each component on the web page cause latency? Let's see the demo. We can see that different objects cause different latency patterns. Image will introduce a short period of latency, and the video may introduce a high period of latency. So the different web pages delay sequence is unique. In our true scenarios, the sequences are more complicated due to the system noise, but we can still distinguish different web pages. In actual, we train a deep learning model to classify them. The final task is to distinguish machine learning model. If a victim is training a model, data will be transferred in and out of the GPU. Like the web page inference task, different layers will transfer different sizes of data at different frequency upon GPU, so different model delay sequence will be significantly different. Here is our experiment and results. In the user input inference task, we have a cycle of 480 watts and use a easy script. We can achieve a high accuracy. Like the prior work, we use HMM to recover the password. In the web page inference task, we collect 100 web pages to infer their delay sequence. And we train classifier attention-based bidirectional LSTM to classify them. The accuracy is above 96% in scenario 1 and above 93% in scenario 2. In the machine learning model inference task, we chose 10 popular machine learning models, 8 DNA models, and 2 simple models. We trained the same classifier. We found that all the models are correctly classified. There may be several ways to mitigate our attack. Firstly, we can block in high-resolution clock instructions, for example, RTTS-EP. But attacker can switch to other instructions, for example, using multiple threads and monitoring the interrupts. The details can be found in our reference list 47. Secondly, we can find ways to detecting suspicious requests. For example, adding a security application on our switch to inspect request sequences, identify the anomalies, and notify data center operators. Another way is to allocate our bandwidth. For example, we can use a virtual channel in the PCIe standard to map physical resources like buffers to high priority transactions, eliminating resource conflicts with low priority traffic. Here is our conclusion. Based on PCIe congestion, we found a new side-channel attack. We developed two concrete attack strategies using RDMA to attack GPU and using NVMe to attack Internet. And also, we evaluate our strategies and inference secrets under 3 victim tasks: keystroke typing, web page browsing, and training machine learning model. Thank you for listening. Any questions?